these are the technologies that we're going to be looking at or talking about. This is what's going to make enable. These are the enabler features for 6G. From ultramassive MIMO, thanks to terahertz spectrum and very high frequency usage, where we're going to get many more antenna elements than there are active devices at any given point in time in a cell, to the fact that we can actually send uplink and downlink at the same time. Uplink means communication from device to the network. Downlink means communication from network to the device. Today, uplink and downlink are separated either in the frequency domain, we call that FDD, or in the time domain, we call that TDD. It is expected that the 6G technology, the advancements in cross-link interference management are so good and so well advanced that we can actually do uplink and downlink communication at the same time with manageable cross-link interference at this, for example, at the cell site. So that's very interesting. It's been a long area of research, and if you have heard about it, non-orthogonal multiple access is on the paper as it is for 5G Advanced today. How are we going to deal with the terahertz challenge is a very interesting question. If the terahertz spectrum has such a big path loss challenge, how can we deal with that? One way is to make use of metamaterials and make reconfigurable intelligent surfaces. These are called RISs, reconfigurable intelligent surfaces. So these can be this can be used in an active mode, where if you put it in front of a transmitter, they can send the signals in any given direction, or they can reflect beams or transmission of terahertz spectrum in any given direction. Interestingly, RIS is a rather cheap and easy thing, relatively speaking, easy thing to manufacture and do. It's a very active area of research, both in the academia and in the industry. And we think that it's one of the most important enablers of the terahertz spectrum. So imagine you're in a mall, and this mall has deployed 6G. You're not just going to have a single cell here and there to cover an area. You're going to have hundreds, if not thousands, of very tiny reconfigurable intelligent surfaces all over the place, disguised maybe behind the walls or in the windows or in other billboards and other things, that can make sure that every single device in a given area benefits from terahertz spectrum in an efficient way. This is not as far-fetched as you might think. And as I said, it's one of the most promising areas of 6G radio network operations. Advanced spectrum sharing, we are already doing spectrum sharing, for example, in the context of citizen band radio, CBRS. On top of that, put artificial intelligence and machine learning. Those are going to be instrumental in allowing us to use very large amounts of bandwidth efficiently. So artificial intelligence is going to be both inherent within the network and as an enabler outside the network, for example, for making things like spectrum sharing becoming very efficient. We talked about computation, the needs for computation. The Apple Vision Pro set that you saw certainly needs to do a lot of computation, but its form factor, it needs to reduce for it to become a commercially viable device that thousands of people use, and it's also at a cheap and acceptable price level point. Today, that Vision Pro thing that I showed you on Apple webpage is actually quite expensive and probably certainly out of my beyond my means to go and get it. So split computation is going to be very important. The ability to have the computation at the edge in the device and intelligently distribute the load of computation between the device, the edge, and the network itself.